Okay, in this video, we're going to be graphing functions. The directions here says identify the parent functions and transformations from the parent functions given each function. Then graph the function using the transformations and identify the key characteristics. Now, as we go through these transformations, here's what we're going to do. Again, we're going to identify stretches, compressions first, flips second, and then all translations last. And that's going to be the order that we do these in. First problem, our parent function is going to be the absolute value function. And the transformations from there is going to be stretches, compressions. We have none. We do have a flip. And then we're going to translate our points right 1 and up 7. Now here's what I've done. I've actually graphed the parent function here. And here's how I want you to go through this. We're going to take some points that are on the parent function. For example, 0, 0, which I know is the vertex, and we should know already where this vertex is going. We're going to perform these transformations, and we're going to see where that point turns out to be. If you take that point 0, 0, flip it vertically, again, that's flipping it across the y-axis, it's still at 0, 0. And then if you take that point, move it right 1 and up 7, it is now at 1, 7, and that's your new vertex. And we already knew that was going to be the case because this one is in vertex form. Now let's take another point. I'm going to take the point 1, 1. Which I know is going to be on the original parent function. We're going to flip it vertically, and that's going to be across the y-axis, or excuse me, that's across the x-axis, and that is now going to be at right 1, down 1. And then if you take that point and you move it right 1, 1 turns into 2. And if you move it up 7, negative 1 will turn into 6. So the point 1, 1 is now at 2, 6. Next up, I'm going to do the point negative 1, negative 1, which is on the original parent function. When you flip it across the vertically across the x-axis, it's now down here at negative 1, or excuse me, that should be negative 1, positive 1. Negative 1, positive 1 is now down here at negative 1, negative 1. If you take that and you move it right 1, negative 1 when you move it right 1 is now at 0. When you take the y value of negative 1 and move it up 7, it is now a 6, so 0, 6. And you can kind of see now the general shape, and you can finish that out, and there is going to be your new absolute value function. And let me erase the parent function now, and let's answer these questions. So therefore, the domain would be all real numbers, negative to positive infinity, and you can get all of these answers from here. The range, the highest value is going to be here at 7, so the range is going to be from negative infinity up to 7, and that 7 would be included. To find your x-intercepts and y-intercepts, I'm going to extend this on, and you see that it's going to cross the x-axis here. It would also cross the x-axis here, and that's going to be at negative 6 and 8, so negative 6, 0 and 8, 0. Your y-intercept is right here, and we found that was 0, 6. The extrema, your highest point on your graph is here at your vertex, and that is the point 1, 7. And that would be, we're going to identify it as well, that would be an absolute max because that's the highest point in your graph. Increasing intervals, here is the cutoff point. So it's going to increase from negative infinity up to 1, and then it starts decreasing 1 forever. In behavior, as x approaches in positive infinity, as we go to the right, your graph is going down. So that'd be y approaches negative infinity. Then as we go left on your graph is also going down. So as x approaches negative infinity, y also approaches negative infinity. Number 2, first off, your parent function is f of x is equal to x to the second. And let's take a look at that graph. Okay, transformations, the only thing you have is the x values being multiplied by 1/4. So that's going to be, we got to reciprocate that. That's going to be times 4, and that's going to be a horizontal on the x, horizontal stretch times 4. And I'm going to write that as an x stretch, just to remind you that the x value is the one that we're going to stretch. I'm going to take my points now. We'll start with the vertex. 0, 0, and all you're going to do, again, you're going to stretch the x's. You're going to multiply the x's by 4. So 0, 0 remains at 0, 0. That's still your vertex. The point 1, 1 would turn into 4, 1. And since these are symmetrical, you could actually already know that 1, 2, 3, 4, 2, 3, that the point negative 1, 1 would also turn into negative 4, 1. The point 2, 4 would turn into 8, 4, which makes us, also tells us, because of the line of symmetry, that negative 8, 4, 1, 2, 3, 4, 1, 2, 3, would also be on the graph. So that would be plenty of points. Here is our new stretched out parabola. That is the graph y equals 1/4 x squared. Your domain and range. Domain is going to be negative to positive infinity, all real values. Your range is never below 0, so that'd be from 0 to positive infinity. Your x-intercepts, the only time it touches the x-axis is at 0, 0. That would also be your y-intercept. The extrema, you have a vertex at 0, 0, and that's going to be your absolute minimum. Your increasing intervals, well, first off, it's decreasing from here to here. So let's say that it's decreasing, we'll start with, from negative infinity up to 0. Then it starts increasing from 0 to positive infinity. Your end behavior, as we travel to the right, as x approaches positive infinity, y also goes up. And then as we go to the left, as x approaches negative infinity, y goes up in that direction as well. Problem number 3, y equals 2x to the third minus 5. First off, your parent function would be y equals x to the third. Okay, your transformations, first off, the 2, that's going to be a stretch. Again, we're doing stretches, compressions first, flips second, and then translations third. So since it's not on the x, inside with the x, that's going to be a vertical stretch. So I'm going to call it a y stretch times 2. And then the minus 5 would simply move it down 5 units. So let's take a point. We'll take our origin right here at 0, 0. And that's going to be, let's perform our 2 operations. If I multiply the y times 2, it doesn't do anything to it. And then if I move that down 5, that is now located at 0, negative 5. And let's plot that 1, 2, 3, 4, 5. And we're going to do that transformation to a couple more points. Again, we're just multiplying our y times 2 and moving it down 5. And I performed it on 1, 1, and 1, 1 actually turned into 1, negative 3. So right 1 and down 3. And then negative 1 turned into, that should have been negative 1, negative 7. So left 1 and down 1, 2, 3, 4, 5, 6, 7. Now let's do one more point. Let's do the point 2, 8 and see where it goes. And multiplying the y by 2 gave me 216, and then moving that down 5 gave me 211. So 211 would be somewhere right around in here. And let's connect our dots, and that's going to be our new function. Okay, domain is going to be all real numbers. That's what you can plug in. What are you going to get when you do that would be the range, which would also be all real numbers. Your x-intercept, now this one's a little tough. I've only got one x-intercept, and just to remind you, to find an x-intercept, you plug in 0 for y, move the 5 over, divide by 2, and to get rid of a cube, you would cube root, or you can use Desmos to find that x-intercept, and that x-intercept is going to be about 1.360, and you can see it about right there. Your y-intercept, the way you find your y-intercept, which is going to be right here, you can plug in 0 for x, or you can see it. This is actually your y-intercept now, and that'd be at 0, negative 5. Your extrema, there are no extreme maximums or absolute or relative maximums or minimums, so we will put none there. Your function is always increasing. It never goes downhill, so we'll say it's increasing everywhere and decreasing not applicable. In behavior, as x approaches infinity or as we go to the right, my graph, y is going up, and as we go to the left, my graph is going to negative infinity, down. Number 4, our parent function is y equals the square root of x. And there, I've graphed that for you. We have 3 transformations. Let's start out with our stretches and compressions. The 3 on the outside would be a y stretch times 3. The negative on the inside will flip it horizontally. That's going to be flip across the y-axis. And then the minus 2 moves it to the right 2. So let's take a couple of points from our parent function, starting with our origin, our starting point there, 0, 0, and let's perform these. We're going to multiply the y times 3, which does not change it. We are then going to flip it across the y-axis. So if you take 0, 0 and flip it, it still does not change it. Then we're going to move it to the right 2, which turns it into 2, 0. Our second point is 1, 1. Let's stretch our y times 3, so it is now going to be at 1, 3. Let's flip it across the y-axis, so that means your x value will turn from 1, 3 to negative 1, 3. And then let's move it to the right 2, so that's going to be just add 2 to your 1, so now that is at 1, 3. So let's plot that, right 1 up 3, so that's going to be now there. So you can tell that your function has flipped over. Let's do one more point, should be plenty. This is 4, 2. So let's perform the 3. Let's stretch the y times 3. That'd be now at 4, 6. Flip that across the y-axis. That's going to be negative 4, 6. And then move it to the right 2 is going to be at negative 2, 6. So let's plot that point. And there it is plotted. And let's go ahead and erase our parent function so that we can answer these questions. Your x-intercept, you have one x-intercept, and that's going to be at 2, 0. And I forgot to do my first couple, my domain and range. My domain, my graph goes from negative infinity up to this x value right here of 2. My range, my graph starts at 0, including 0, and goes up forever. My x-intercept was at 2, 0. My y-intercept was right here at 1, 2, 3, 4, so 0, 4. My extrema, the lowest point on my graph, was here at 2, 0, and that's going to be the absolute lowest point on my graph, so the absolute minimum. There's no maximums there. Increases from left to right, your graph is constantly going downhill, not uphill. So it's never increasing. That's not applicable. However, it's decreasing from negative infinity all the way up to its stopping point here at 2. And that is always open interval. And our end behavior would be, and this is going to be a little bit different because if we look at our domain, the end is actually, it goes to 2, not to infinity. But as x approaches 2, my y value approaches 0 there. So that's one end, and the other end of your function goes to negative infinity, and as we go to negative infinity, my y value goes up, would be our two end behaviors there. Okay, number 5. First off, our parent function, f of x is equal to the cube root of x. Identify the 3 transformations here. Since the 2 on the inside, that's your multiplication, that's going to be a horizontal or an x. Okay, stretch or compression, you do have to flip it since it's on the inside, so that's going to shrink it. So we're going to write that as an x shrink times 1/2 times the reciprocal. And then we just got a couple of translations. The plus 1 inside would move it left 1, and the plus 4 would simply move it up 4. So let's take a couple of points. Let's graph our parent function. Okay, now let's take a couple of points, 2 or 3 points off of our parent function, 0, 0 being 1, and let's perform these operations. X shrink times 1/2 means you're going to take your x value, multiply it by 1/2. Then you're simply going to take that point and move it left 1. So move the 0 left 1 and move the 4 up 4. So the 1, 1 has actually, or 0, 0, 0 actually turned into point negative 1, 1, 2, 3, 4. It is now located there. We'll now take the point 1, 1 and multiply the x value times 1/2. So that is 1/2 1 now. And move it left 1, so that'd be at negative 1/2. And move the 1 up 4, that's going to be at 5. So negative 1/2 comma 5 would be located, go over half a box and up 1, 2, 3, 4, 5 boxes. You can do the same thing with a couple more points, and we'll do that for you. So there we've kind of done a couple more points for you, and I went ahead and connected the dots there, and there's your transform graph. Domain of your new graph would be from negative to positive infinity. The range would be down forever and up forever, so it'd be the same, all real numbers. X-intercepts. Again, in order to find that x-intercept, you can set your function equal to 0, move the 4 over, cube it, divide by 2, and subtract 1, and you should get negative 33, 0. Your y-intercept is located right here, and again, you can always find your y-intercept for plugging in 0 for x. So 0 plus 1 is 1 times 2, cube root of 2, type it into your calculator and add 4 to that, and you're going to get 0, 5.26. Okay, your extrema, the highest or lowest point, notice that it has no upper maximums or minimums because there's no high or low points on the graph. It continues up and down forever. So there are none. We'll just put none instead of not applicable. There are none. Increasing intervals from left to right, it always goes uphill. So therefore, it is always increasing and it is never decreasing, not applicable. Your end behaviors. As you travel to the right, as x goes to infinity, your y value goes up. As you travel to the left, your y value goes down. Next one, parent function. It's going to be f of x equals 1 over x. Let's take a look at the graph. Okay, now let's examine our transformations. Notice that you have taken your whole function and you multiplied the top by 4, which would mean you took the whole function multiplied by 4 over 1. So it'd be vertical, because it's not just to the x, it's to the whole thing. So we're going to do a vertical stretch or a y stretch times 4, and that's all your stretches and compressions. Now the negative, you can look at it either way. We'll go ahead and say that because that negative could be placed on bottom as well, but we'll go ahead and do a vertical flip, which would be a flip across the x-axis. And again, if you'll think about that, if you're going to flip something across the x-axis, that means your y will change from either positive to negative or negative to positive. And then the last one, that plus 3 on your x value, will simply move your graph left 3 units. And let's take a couple of points. And honestly, if we can get this point right here and this point right here, because we've got asymptote lines here, we can kind of figure out what the rest of it will look like. So let's take the point 1, 1 and negative 1, negative 1 and see where they go. Okay, first off, 1, 1. We're going to flip, or we're going to stretch the y times 4, so we are now at 1, 4. We're going to flip it across the x-axis, so that's going to be 1, negative 4. Then we're going to move it left 3, so that's going to be negative 2, 4. So this dot right here gets moved to negative 2, 1, 2, 1, 2, 3, 4. So it's going to get moved up there. Now let's see what happens to negative 1, negative 1. We're going to multiply the y by 4, so that's going to be negative 1, negative 4 now. Let's see, we're going to flip it across the x-axis, so that's going to be negative 1, positive 4. And then left 3 will be at negative 4, positive 4. Okay, let's pick a couple of points and see what happens. Let's get this point right here, which is located at 1, 1. Okay, we're going to multiply our y by 4, so that turns it into 1, 4. We will then flip it across the x-axis, so that'll turn it into 1, negative 4. And then when you move it left 3, that's going to be negative 2, negative 4. So left 2, down 1, 2, 3, 4. So the point 1, 1 went from here to here. Now let's try the point negative 1, negative 1, and I'll go through the steps for you. And it ended up at, from negative 1, it ended up at negative 4, 1, 2, 3, 4, 1, 2, 3, positive 4, negative 4, positive 4. So there's those 2 points. I'm going to pick a couple more just to see what's going to happen. I'll pick the point, let's see, this is 2 comma 1/2. We'll try it next. So 2 1/2 turned into -1, -2 right here, and I went ahead and did -2, -1/2, and it turned into -1, 2, 3, 4, 5, +2. So now we kind of get an idea of what our graph's going to do. It's going to look something like this. Let's try that again. Here and here would be our new looking graph. We do have an asymptote line, and the domain before we had an asymptote line at 0. Now our asymptote line is going to be over here at, actually I drew it a little bit off. It should have come up and did this number, and that asymptote line is going to be, I'm just going to put x can be anything except for -3. The reason for that, we see that x can't be a -3 because then we'd have division by 0, and that's what's going to create this asymptote line right here. Your range, your y values can be anything except for 0, because again your graph kind of levels out right here, so y is going to be everything except for 0. It's going to be an easy way of putting that. Therefore, you're not going to have an x-intercept, because if y can't be 0, then it's not going to cross. You do have a y-intercept right here. And again, the way that you can find that is by plugging in 0 here for x, and you would get 0, comma, -4/3. Very easy to plug in. Your extrema, since it's going down forever and up forever, let's see, it would be hard to have an extrema because down forever and up forever, and it never levels off. It never comes back down, so there are no extrema there as well. Increasing, okay, you're increasing from -infinity up to this asymptote line, so increasing from -infinity up to, that was located at -3. But also then you jump down here and you start increasing again, and you increase from -3 to infinity, and your graph never decreases in behavior. As you travel to the right, your graph starts again leveling off, and it gets closer and closer and closer to this x-axis. So your y approaches 0, and the exact same thing happens as you go to the left. Number 7, your parent function. It's going to be y equals the cube root of x. Let's sketch that out. Okay, let's talk about your transformations. Here's your only stretch or compression. Since it's only x, we do have to flip that, so that's going to be an x stretch, because once you flip it, you're going to get 3/1, so that's going to be x stretch times 3. The negative is going to be a horizontal flip, so that's going to be a flip across your y-axis. So that's going to change your x positive or negative. And then the +4 on the end is going to move it up 4 units. Now let's take a couple of points from this graph, and I'm going to do the work for you. Let's transform them. Okay, here's the transformation. 0, 0 turned into 0, 4. 1, 1 turned into -3, 5. -1, -1 turned into 3, 3. And I've plotted those 3 points, and here's what your new graph will look like. Okay, so your domain will be all real numbers. Anything can be plugged in. Your range, this graph will increase to the left and decrease to the right forever, so it will be the infinities as well, all real numbers. X-intercepts and Y-intercepts, again, to find an X-intercept, and we'll work this one out for you. To find an X-intercept, you're going to set the entire thing equal to 0. We're going to move our 4 over, so that would give you the cube root of -1/3 x is equal to -4. To get rid of a third root, you're going to raise the other side to the third power. That'd be -4 to the third, which would be a -64. Now to get rid of -1/3, we've now got to multiply the other side by the reciprocal. So multiply by -3 would give you a 192. So your x-intercept is going to be at 192, 0. So it flattens out, but it's going to take it a while to get to that x-axis. Here's your y-intercept located at 0, 4. There's no extremes, no high or low points on that. Your function is continuously decreasing, so it's never increasing, but it is decreasing from negative to positive infinity, your end behaviors. Now, when you're dealing with cube root functions, this thing does, again, continue going down and continue going up forever. So therefore, there are no asymptote lines. So as x goes to positive infinity, your graph, your y value approaches negative, it's going down. As it goes to the left, your y value is going up, approaches positive infinity. The next one, number 8, your parent function is, again, y is equal to 1 over x. Your transformations, you can think of this 2 is going to get on the bottom by multiplying your whole function by 1/2. That would force that bottom to be a 2. So you could say that's going to be a vertical stretch times 1/2, or a y stretch. Or that would actually be a y shrink because you're multiplying by 1/2. A y shrink times 1/2. So we're going to shrink our y's by 1/2. Then the -1 on the end, that's just going to simply move your function down 1 unit. So I'm going to take a couple of points. Let's look at our original graph, and I'm going to take a couple of points for you and do some transformations. So there's your parent function, y equals 1 over x. There's a couple of points that I took off the original. 1, 1 transformed into 1, negative 1/2. So that's going to be about right there. And negative 1 turned into negative 1, negative 3/2, which would be negative 1, negative 1.5. Now I'm going to do the exact same thing, pick a couple more points to make this graph look a little bit better, and let's look at what the transformation is going to look like. Okay, so I took a couple more points and translated and transformed them, and just pointing out that my asymptote line, my horizontal asymptote, my x or my y value will never be there. My x value you can actually get from the original. X can't be 0 because if you plug in 0, you're going to have the division by 0. So my domain, x can be anything but 0. My y value, again, my y value will never be negative 1, and you can see that from the graph. My x-intercepts, I do have an x-intercept right here, and we can find that by simply plugging in or setting this thing equal to 0, move the 1 over, and do the operations there, and you're going to get that you have an x-intercept at 1/2 0. Your y-intercept, again, this thing never touches the y-axis. The y-axis, so therefore it's not going to cross it. Because x is never equal to 0. So therefore, they will have no y-intercepts. Extrema, there's no extreme high points or low points, so there are none. Increasing, my function is decreasing, and then it comes up here, and then it starts decreasing again. So there are no places where it's increasing. However, decreasing, we're going to decrease from everywhere from negative infinity up to this value right here, which was 0. And then we jump up top and we start decreasing again from 0 to positive infinity. End behaviors, as we travel to the right on my graph, my y value tapers off right here at negative 1, and it does the same thing as we travel to the left. Number 9, my parent function is the absolute value function, so absolute value of x. Let's take a look at the original parent function. Okay, now let's talk about the transformations. We do have some multiplication happening here on the outside. So that's going to be a vertical compression because you're multiplying by a 4. So a y shrink times 1/4. Then the +2 and the +5, those are going to be translations. The +2 is going to move it left 2. The +5 will move it up 5. So let's take a couple of points for our original and see what happens. Okay, so here I chose 0, 0, which was my vertex, and my 0, 0, I'm put that in the wrong place. My 0, 0 is actually going to move to, let me erase those. 2, 6 was right. 0, 0 is going to move to negative 1, 2, 1, 2, 3, 4, 5. That's going to be my new vertex. I translated the point 1, actually 4, 4. Let me tell you why I chose 4, 4. I knew I was going to have to multiply my y value by 4, so I knew if I chose 4, 4, a fourth of 4 is going to go to 4, 1. Then left 2 and up 5 from there was going to be 2, 6. So there's my 2 points. This being my, again, my vertex. So I go up 1 and 1, 2, 3, 4. So I can go up 1 and 1, 2, 3, 4 here and use my rules for absolute value functions to where those 2 points are actually going to be plenty for my function. My domain will be all real numbers. My range, my lowest point will be my vertex. So my range is going to start at 5 and go to infinity. My x-intercepts, there are none. My y-intercept, it does cross here. And to find that y-intercept, again, we simply plug in 0 for x. So you'll have the absolute value of 2 is 2. Take a fourth of that. That's going to be a half plus 5 is going to be at 5.5. So 0, comma 5.5. And you can see that's about where it crosses right there. My extrema, I do have an absolute minimum at a vertex, and that's going to be, again, located at -2, 5, and I'm going to put that that is an absolute minimum. My increasing interval would be from here over. Again, that's going to start at my vertex, which was at -2, so I'm going to increase from -2 to infinity, and I decrease from negative infinity up to that -2 because it was downhill over here. My end behaviors, as we travel to the right on my graph increases without bounds, so y goes to infinity. As I travel to the left, we're going up as well, so as x approaches negative infinity, y approaches positive infinity. Okay, number 10, our parent function is y equals x to the second power. Let's take a look at that graph. And we see there our parabolic shape, our transformations, all of our stretches and compressions first. We do have a vertical stretch times 3, so we'll call it a y stretch. Just so we'll remember to multiply it times our y, and that'll be times 3. We have a negative in front, so that's also going to be a y flip, an up and down flip, so that's going to be a flip across the x-axis. And that does always change your y value whenever you flip it that way. And then the last thing would be our right 4 because of the x value there, and then up 6. So we'll put right 4 and up 6. Let's take a couple of points and transform them. Let's see, I'll pick 0, 0 since that's our vertex, which before I do anything else, we already know where 0, 0 is going. It's going right 4 and up 6. This is in vertex form, so we can go ahead and put 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. That's going to be our vertex of it. And what I would do is I would transform things maybe to the right of that because we know the symmetry, the properties of symmetry, the line of symmetry whenever we're dealing with a parabola. So maybe transform 1, 1 and 2, 4 would be 2 good points, and then we can use our line of symmetry to actually find the points on the other side. Okay, after these transformations, my 1, 1 turned into 5, 3, which you can see the dot here, and my 2, 4 turned into 6, -6. And since I know that my parabola is symmetrical, here's my line of symmetry. I know I'll have a point here, and here's my line of symmetry, so I know I'll have a point over here connecting my dots, and there's my parabola. Okay, my domain, there are no restrictions, so my domain is going to be all values there from negative to positive infinity. My range is all values up to this y value here, which is my vertex, so that's going to be all values up to 6, so that's going to be from negative infinity up to 6, including my vertex. My x-intercepts, I should have a couple of them. Let's try to find those. And all we'd have to do to find those, and I'm not going to work it out, but you'd set this equal to 0, move the 6, divide by -3, take this plus or minus square root and add 4, and you should get 2.56, 0, and 5.41, 0. Your y-intercept, you simply plug in 0 for your x value. 0 minus 4 is -4, squared is 16, times -3 is -48, plus 6 is -42, so that'd be 0, comma, -42 is your y-intercept. You do have an extreme value at your vertex, and again, it was located at 4, 6, and that was an absolute max. Your function increases everywhere up to that x value of your vertex, so that'd be from everywhere from negative infinity up to 4, and then it starts decreasing, and it decreases on the other side of that 4. Your end behaviors, As we travel to the right, our graph goes down. As we travel to the left, our graph goes down. So both of our y values in both directions would approach negative infinities. Number 11, we have our floor function here. So f of x will equal the floor function of x, or again, you can use the other notation as well. And let's take a look at that graph. Well, we've got some pretty simple transformations here. We're simply moving it left 1 and down 3. So let's take some points. Let's take our 0, 0. And if we move it left 1 and down 3, we are now at negative 1, negative 1, 2, 3. And even this open circle, it's going to move everything left 1 and down 3. So even the open circle on the other side is going to move left 1 and down 3. So your new function is going to be pretty straightforward. It's going to look something like this. So open, close circle, and just connect them. So it'll look something like the blue function. Our domain would be all values. There's no restrictions there. Our range, notice that again with the step function that there's nothing in between. So our range will be just my integers. My x-intercept, and this is actually an odd x-intercept because my new function crosses the x-axis everywhere from 2 over to here. So I'm going to actually write my x-intercept as all values from 2 up to 3, not including 3, just because I have an open circle there. So my function is everywhere on that x-axis from 2 up to 3. My y-intercept is right here at 0, negative 2. Extremas, there are none. There's no maximums or minimums. Okay, now let's talk about whether the function is increasing or decreasing. Now, this is an odd function to talk about because if it's increasing anywhere, let's look at this. From this point to this open circle, we actually have a constant function. Then it jumps up here. So if it's increasing anywhere, it's increasing at the integers, at the whole numbers. And then decreasing, and this function never decreases, it never goes down, so we're going to put NA. In behavior, as we travel to the right on our graph, notice that we are always stepping up and going up and going up. So as we travel to the right, your y value is approaching infinity. We're always traveling uphill, and then as we go to the left, we're always going down. So therefore, that'd be y would approach negative infinity. Okay, number 12, we notice again our parent function is our greatest integer function. So f of x is equal to the floor function of x. So therefore, let's take and plot a few points. And there's a good bit of our graph. Now let's look at our transformations. We have a 2 on the outside, and that's going to be a vertical stretch times 2. The negative on the outside will flip it vertically, so that'd be across the x-axis. And finally, the -4 and the +1, those would be your translations. So that's going to translate it right 4 and up 1. So let's take some of these points and see what happens to them. We'll take this point here, which is located at 0, 0. And we'll take a couple more points, maybe 1, 1 and -1, -1, and see what happens. So 1, 1 and -1, -1. Okay, so we've plotted these 3 new points, which occur at 4, 1, 5, -1, and 3, 3. Now you've got to be careful with this because we flipped across the x-axis, which means this pretty much is just going to flip down here. So you've got a solid circle that goes to the right to an open circle. Now, had we flipped this across the y-axis, it would have kind of flipped that over backwards. So you'd had a solid circle going left into an open circle. So this is going to remain the same. So we just kind of do this here, this, and this would do the exact same thing. However, it did stretch it up some, so you do have a larger gap between your steps, but it looks very similar to what it did before. So the red now, and I'm going to erase the purple, but the red is now your new graph. Now let's go through the steps, the domain. You can plug in anything you want to, so that'd be all real values. The range, however, notice that you only have graph here and graph here and graph here. That'd be 1, 3, 5, -1. That'd be all your odd integers is the only y values that you would get. So instead of writing that out, we could put our integers are going to be our z's. So our odd integers. Our x-intercept looks like there's nowhere on the x-axis where we cross. Your y-intercept, if you were to continue on up, we would have a y-intercept. And you could, like I said, you could take another couple of steps up, and you could see that that y-intercept would be, it would occur at 9. Extrema, there's no max or min points. Increasing intervals, again, now you see this thing going downhill. So increasing, there would be none. And if you're going to put a decreasing interval, the only place that this goes down is from here to here. So if you're going to say that it decreases anywhere, it would be actually at the integer values. Because again, it would jump from here to down here, or from just to the left of the integer down to the next integer. End behaviors. So as we travel to the right, notice again that my graph goes down. So y would approach -infinity. As we travel to the left, my graph goes up. So y would approach +infinity.